Yes, good afternoon, everyone. Well, let me start sharing the slides right away. I think it will be easier to go with them. Actually, I sent you a request. I have extensive access.
Yes, I approved the request.
Yeah,
Everything is fine.
let's remember. Okay. Yes, let me start here. Well, good morning and afternoon, everyone. Depends on who is where. My name is Nikolai. I'm a software engineer at Instagram. For the past few years, I've been working on mobile app optimization, and in traditional software, it's generally divided into three axes: performance, reliability, and efficiency. Yes? Today I want to talk about the practices already used in existing software and in traditional software, and how they can be applied in a world where artificial intelligence has already emerged. Actually, we've already passed the stage a little bit when all this was new, yes, and agency systems, workflow, all this was emerging, and people were just looking for some kind of product market fit, trying to understand how in general, how to find out where these models are applied. Well, just like in traditional software, many companies have already reached the stage where they have built this into their pipelines, and some have built new products, and we are already moving to the stage where all of this is scalable, because it already has a specific value. And then comes the moment when you need to seriously think about optimization and understand how it will all work across a huge number of users or use cases.
As I have already partially mentioned, optimization is usually considered along three axes: reliability, efficiency, and productivity. Reliability. Here everything is clear, that how correctly we solve the problem, yes. Efficiency is how effective it is and how much it costs us. Performance is how fast it is. And in the world of agent networks, there's a lot of talk about reliability, because with them comes enormous non-determinism, when we have no guarantee that, for different inputs, we will get the same result or that it will always be sufficiently correct. Well, in software, it was like this. It either works or an error is thrown, and everything is very clear. Here we have all these, there, eval on the finalization of prompts, and, in general, everyone is already actively monitoring this. This one has high visibility. With efficiency, in general, there's also such a small shift. It was always in sight, too, because it was real money. But here it has become even more transparent, because we have tokens that are worth specific dollars, and everyone can immediately see how much requests cost. And this third component, which I want to talk about a little more today, is performance. It seems like they are talking less and less about her. Well, more precisely, it's not really affected that much. Even in traditional software, it is often relegated to last place because it is more hidden and we do not have any obvious problems. Yes, we don't have any crashes. There are no bug reports, often because the application is slow, and because of this, there is some kind of understatement and some value is left on the table. Here, in some scenarios or like in agent networks, they are very insensitive to performance. What can I say? We are sending some task. He went there, in the background somewhere, to work through all of this. He returned to us an hour later, and, in general, the problem was solved, and we were happy. And this is considered generally cool. This is the height of performance. There are environments where you have a more linear pipeline, quadruple A, and people see multitasking as a bug rather than a feature. Here, where the cost of error is high and they need to focus on the specific problem they are currently solving. As an example, I would like to give you a product, let's say, that we are developing, in which we help, solve the billing problem for hospitals. Yes, let's say, at each discharge, yes, when we discharge him, we need to verify that all the data that we have there, that we requested from him, has been added there, from the patient. We need to understand that we have everything indicated correctly, there, the diagnostic codes, what is shown, there, the patient's card was written down correctly. We asked the right questions so that later there would be no questions from the insurance company, that they understood correctly, that we did everything correctly, everything was according to protocol, and everything was working. Let's say a nurse in a hospital interacts with such a system, and before each discharge, yes, of a patient, she will come up and fill out this system. And so, for each such request, she will essentially stand and wait until the system finishes working. Here. And at that moment, you won't be able to do anything else useful. It immediately becomes clear that in such systems, this is not just a problem, their user experience, it is a problem of the system itself. Yes. How many patients does she have the capacity to serve? Because like one such hang up for, there, an additional, there, even 90 seconds or, there, a minute, it, there, 2 minutes, it quickly scales up. Because we are not solving this problem for a specific, yes, nurse. If we supply software, it most likely goes to a hospital, or perhaps a city, a county, and so on. And this very quickly adds up to an additional load on the system. We need more staff or we cannot serve the required number of patients. In general, this is all, it all accumulates. And chances are, this may not happen for all of your patients. It can only happen for a certain category. And for them it will be, there, a bigger problem than for others. It will be hidden for you, but since you're still solving what seems to be the key problem for this, your client, they might not even complain about it, will continue to use the product, although in doing so, we can create a kind of bottleneck where there was none before, and this can have a negative impact on the system itself. Our assumption often turns out to be wrong about how the product works. It's clear that we always try to look at product data, but when it comes to evaluating performance, yes, speed, it's always product data. Here, because we have a huge number of use cases and features, and it is necessary, we must always try to tie it into the data that we collect from our system. So the first step and the most important thing is to instrument everything. There are many open source projects that help do this. Track them and see the prices. There, scoring, they help with eval. And there are commercial solutions, of which there are also quite a lot. All this can be done, as it were, by studying what is on the market, without necessarily building something of your own. Moreover, the industry is, specifically, agency networks. It has become a little more accessible because the problem of this very thing, reliability and efficiency, is more acute. And these tracing systems have become a little more, accessible, because in traditional software, very often the most advanced systems are developed in-house. It's kind of difficult to, reproduce something like that from the outside. Here, so yes, tracing itself is not something new, but what is new about it is these pipelines, which are super non-deterministic. Because, the more complex our system is, the more it can involve other, sub-agents or some kind of tools, and they can solve a problem in very different ways. Because of this, how long this task can continue to run, how many tokens it will consume, and so on, varies greatly in different scenarios. That's why we always, when we evaluate performance, we look at percentiles and distribution. That is, percentiles. This is, in essence, in short, if we have P50, this is our median user, the median scenario. That is, 50% of the scenarios are processed like our P50. If it's, say, 2 seconds, it means in 2 seconds or faster. Then we have the next 75, 90, yes, 99. And we always try to optimize the end of this distribution, because our edge cases are at the end. Here, at the same time, we still have, as it were, certain cutoffs, beyond which we do not rush to go, because they could be too much. It could just be noise. Something didn't work there. The system was down. Therefore, there is no point in getting hung up on anything higher than the 99 percentile. But they're P90, P95, 75, depending on your system. That's where you need to look. Another very important detail that doesn't happen often is that, in addition to the fact that you are provided with these frameworks and standard traces that you use, You also need to enrich all of this with your business context. Yes, and understand what your tasks are and how you solve them. So, in our specific example, where we are now, running this presentation, this is, for example, a hospital or a state where this is happening, right? We can add some data like this to each trace. And then, later on, when we get to analytics, this can show us some very valuable asymmetries in our data by which we can judge that some inefficiency is occurring. Specifically, in this example, we can imagine that we have several states for which, as it turns out from the traces, the execution time is much higher, maybe 3 times higher. And if it was just some distribution noise without this division, we would just see, well, there are some that are slower, there are some that are faster. But as soon as we have these additional attributes, and we can trim them, we will have some kind of mental framework. And so, by adding these attributes, say, of the state, we can see that in some states we process longer and we can guess, based on individual traces, that our agent, for example, goes and pumps out some additional regulatory context, for himself. And this happens dynamically because the agent is independent. He realized that he is missing something. I took it, went to the internet, read this file, an additional cool tool, additional network latency to open this site, download all this. We can simply take all this data, yes, put it to ourselves, connect some cron job that will synchronize this data once a week, once a day, because the regulations do not change often, and we will, push this entire context through RAG, yes, at the beginning of the system prompt. And with this, we can do more than just solve the problem and remove additional cool tools. We can also put this entire large context right away into the system prompt, and therefore, at the beginning of our prompt, and therefore, essentially, into the cache. Because, well, the way the cache works is that, yes, the first part, which if it doesn't change, it all goes into the cache. We cache the last token, and then only what happens after this last token is not in the cache. Specifically with this example, this at the same time we killed two hares, or as they say here, 2 birds with 1 stone in English. Yes, they say. In general, we are not only solving the speed problem, we are also solving the problem with tokens and caching at the same time, most often. And it turns out that we can reduce specifically for these traces of specific states, latency there with, there by half. Essentially, by using this kind of trace analysis, one company I spoke with, they actually managed to significantly reduce both costs and the duration of the solution. They changed the model and their reliability. Yes, it also increased, because there is always a certain percentage that they understand that it exists, but they cannot solve it simply by modifying the components. The last couple of points, perhaps, that I would like to mention is that optimization is not some kind of one-time action. It is a process that needs to be built in, which is simply cyclical. You need to add more tools, add some data attributes when you understand what is important for the business or what can influence. There, time zones, maybe, yes, that could be. It could be some kind of load on the system when you have peak hours, when everyone comes. I don't know, early in the morning to the hospital or something else. It is very important to monitor how your data changes over time, how it potentially regresses, optimize, and analyze. In general, there is one C cycle. We had logs, observe what is happening, analyze, and optimize. If I were to leave some kind of AAA message from this report, it's probably that if you don't do anything at all in your company, you only count the top line. Start by simply instrumenting at least 1 or 2 flows that are the most critical for you, where the largest volume is. Just add basic tracing. The tools exist. You don't have to change your entire infrastructure just to support these 2 scenarios. At least just do them and get the first data. If you already have some frameworks, you use LangFuse, do eval, something else. Try adding business attributes, because this is something that people don't seem to pay attention to. They simply do the standard things that frameworks provide and try to analyze them. There, again, they focus exclusively on reliability and efficiency. Look, from a performance point of view, this could be very interesting. Well, yes, always look for asymmetries. We need to focus on the end of the distribution, look at outliers, at edge cases, and try to understand how this works for, say, the 10% worst cases, and try to find ways to isolate not individual user problems, but clusters of problems within a group using attributes. Well, that's all, I guess. Thank you for your attention.
Thank you. Thank you. Interesting report. Now, perhaps, let's move briefly to the questions.
Can I ask, yes?
Yes, yes, yes.
So, hello. It was very interesting. Can you tell me what bottlenecks you encountered when scaling your workflows? And how did they solve them? Maybe the AI was helping.
Specific examples of optimization are the question of how to set up the process itself.
No, I'd like to talk about specific examples, if it's not too much trouble.
Well, specific examples. Here's one that I brought here. It was, well, just an understanding of the location. Yes, some specifics. That is, what can specifically affect, in the example, the network performance. That she can understand that she's missing some context, right? That is, when we cover something with an agency solution, we most likely think that we have a rough idea of what the problem is and how it can be solved. We are trying to encapsulate it, yes, in some kind of block, to set some boundaries around which this system will act on its own and try to operate. Therefore, we build some sub-agents, we build some specific ones there. We set these prompts, but sometimes it goes beyond the limits. And this going beyond the limits is not always visible, as if, in essence, on the eval, yes, which monitors reliability and can be seen in efficiency. But again, if it solves a problem, we usually look at efficiency more, as if on some average value. Here, in these examples specifically, probably, are all about how attributes add. That is, location, time zones. I also gave an example. It seems to me that this is very often a well-scalable example for different things, because, well, yes, you can group, as if we just have time, but you can sort of group this time and try to understand at what time of day it happens, in what shift this happens. In the example we discussed, this can also be very important and useful. It can be understood that some data, for example, we have some time during which there is too much load on the system. It can be very useful to simply make some kind of request to the system in advance. That is, if we understand that there is also an optimization batch for different agents, if we understand that we do not change some data there for a long period of time before we need this data itself, well, you can just go and make these batch requests. The main thing is to simply understand when to do them, because they are kind of talked about. But this identification, when it is really useful, it can sometimes be visible due to the fact that we actually have a peak load there and our servers are crashing at a specific time. Yes, we see that this is happening consistently for some reason. You can adapt to all of this if you have the data in front of you.
Understood. Thanks a lot.
Thank you.
Hello.
Yes.
Thank you very much for the report. I have a question. What does the architecture of modern AI systems typically look like in practice? That is, what key components does it consist of?
Well, look, here we probably have the following issue. Our systems are built to meet needs first and foremost. And in fact, what is meant by advanced is a vague concept, because in my understanding, it's very important not to go into these systems at all when, for example, they are not needed, right? They need the main rule, to simply understand whether this problem needs to be solved with artificial intelligence or not. So we can start with just, like, if it can be solved algorithmically, it is better to do it algorithmically. It is more deterministic, more understandable, and we need to strive for that. It is clear that if this is not possible, then somewhere one request will be enough. This system will have much higher reliability, from the point of view of implementation. If it is some kind of single call, there is an LLM call. We just went. We have a specific task. It's easier for us to evolve it, and it never, not like it goes rogue. Yes, it doesn't go and start using some tools, snarling the web there, and doing some tasks that we didn't expect it to do. Then we have these pipelines, yes, AI workflow. When we have some execution going on sequentially, or even if it is parallelized, we still decide ourselves, as it were, which node follows which. Well, like a point, right? That we will first work on these, then those, and then we will merge all of this. Well, in essence, this is what, probably, the most complex systems are, right? When we have some kind of agent, which is an orchestrator or whatever you want to call it, which has other sub-agents under it and there are systems where these sub-agents are predetermined, but it also happens that this super agent, the supervisor, he himself dynamically creates sub-agents to suit his needs and solve certain problems. And it's like, the more of these elements, each of them is a point of failure, right? If each of them has a 95% chance of reliability or some kind of latency, then these 5%, they compound as if constantly. And as a result, our system becomes less and less reliable. And this trade-off, which I would like to talk about here as much as possible, because, small mistakes, they are inevitable at least in the current incarnation of these systems. As far as I understand, I'm not saying that I was, doing some kind of ML research there. They are like hallucinations. They are part of the system, and we solve it solely by having the agent grounded for something, and he makes fewer mistakes. And even if we talk about simply fundamental models, they seem to exist in the same paradigm. Therefore, this percentage of these errors is always there. And it is very important to us that these moving systems are minimized. I don't know if I may have answered the question incorrectly, but if we take more complex ones, then yes, there are agents, sub-agents, they have tools, they have skills, and so on. And all these capabilities of this system, they, in fact, add both additional load and additional non-determinism of the result, which is exactly what we want.
Yes.
As if.
Can we say that DevOps is the foundation for AI?
You can probably look at it from this side. Exactly. Because it's the same, in my understanding, it's the same software block, like any other, just with its own specifics, and I think that's how we should treat him. And it's already in general, like, if we're talking about, well, DevOps, as far as I understand it all, like we already have everything, the whole infrastructure, it's already cloud-based. It came there right away. For us, this is not the same as how traditional software developed. And yes, well, I think that most of the practices are applicable here, and it's just a question of how we probably measure, in short, all these, use cases, scenarios. They probably don't quite map into traditional methods either. Not completely, because we still have this unique problem of non-determinism, the problem that this system is, like, more difficult to evaluate and track. We often track it there with other models. Yes, using more complex models so that they are cheap to determine. But this, as far as I understand, from what I've talked to specialists in this system, in this one, in DevOps and FinOps, this is a largely unsolved problem because everyone is rushing towards the need to build and use AI wherever possible, but they still don't have time to properly track it. That's right, even from the point of view of efficiency, right? In large companies, this is still a problem. Who was I talking to? That is, there is an understanding of the top line figures of how much we spend on all of this, but there is a poorer understanding of what exactly, what components, and where specifically in these components it is ineffective. There are simply some upper levels that are larger in budget than some specific things here, and this is what we need to come to.
Thanks a lot.
Thank you.
Thank you, Nikolai. Good report. Hey, let's move on, because there are a lot of people, and there are a lot of questions too, but we have a short schedule, so guys, please keep your questions a little shorter so that everyone has time to ask and answer. Well, then, World, the floor is yours.
Thank you.
Well, I'll continue then. Nick, thank you. Nick touched on the topic of efficiency. I'll continue it a little in a slightly different context. Real-time AI a latency issue. Let's start with what real-time AI is. Yes, real-time AI can be anything. These could be some kind of sound interfaces. This could be some kind of AI that is used in games. Extended reality. Basically, anything you communicate with right here and now. Request data right here and now. And you need it fast and efficiently, here and now. At the moment, AI models are growing very quickly, and, their, quality, their processing speed, compute, yes, everything. Everything is growing many times over. At the same time as, infrastructure, has certain limitations. Therefore, the problem arises that the AI is fast. Yes, it calculates everything, but the product, unfortunately, works slowly. Yes, there is a good example here. The engine is shown on the left. That is, this is a block on which artificial intelligence is calculated. There is memory, there are different cool modules, and every 6 to 9 months, this engine doubles the amount of parameters it can handle. That is, the speed at which AI is growing is simply unreal, yes, and AI is evolving very quickly, and we all see it. Models are getting smarter, everything is getting cooler. But unfortunately, we still see this experience, yes, infrastructure problem, when we ask something to the AI, and then sometimes wait, maybe, half a minute, a whole minute, perhaps, for an answer. Why does this happen? The thing is that AI is just one step. It's just one layer in this whole system. That is, as I showed before, there is such an engine. Yes, this is a large block in which a bunch of different calculations take place, a bunch of different layers. Here it is shown that everything starts with request. Yes, and Nick touched on this topic that there are some requests to the network that are being processed. They contain this very latency. Then all of this is put into a queue. There is some internal business logic in which all of this operates. Some, if it is, in this case, in this context, an example is shown, a RAG system, which embeds some additional data, some documents, perhaps, or some, supplements the request with some search, perhaps on the internet. Here too a vector database is used, so the process is quite long. For each of these stages, a certain amount of latency, additional delay, is allocated. Here, it is shown that, the fastest AI engine, yes. You can have super mega memory, super fast compute, super cool video cards. No matter how powerful your AI is, no matter how powerful your AI model is, you can still get stuck on east-west network traffic. East-west is a term that I don't know who is familiar with. East-west is a term that refers to the interaction between servers, and there is north, north-south. This is when the client connects to the server. Here, in general, now everything is moving towards sharing data between servers, rather than when a specific client, connects to specific servers and works with them directly. Let's look a little more closely at the anatomy of a 2-second delay. Let's imagine that we have a 2-second delay. Let me clarify right away that in this case, we are talking about some kind of RAG system that will additionally embed some content. So, in the example, we spend 1/4 of a second on serialization. Yes, here is an example, not the best example, when we use REST and JSON serialization. JSON serialization is quite slow. Here it takes exactly 1/4 of a second. Next, a search is performed in the vector database. Next, sorting and ranking occurs based on the output from the vector database. Here goes a very famous, very well-known metric. For those who don't know, time to first token measures all this pre-filled data. That is, when we, in general, in short, yes, how LLM works, who doesn't know? We initially go through this whole long journey before we start generating the first token. And now the time to first token is this whole pre-fill process. There, the bottleneck itself is often involved. This token, how it is generated. Bottleneck is a compute here, and then you can see this blue part, token generation. There we are already limited by memory, and we simply predict each subsequent token. Compute is also important, but now we will have a limit. The bottleneck will be in token generation. And of course, this is the biggest part, because most often we have many tokens, not just one token. If there was one token, we would have finished with this already. For those who don't understand, again, a token, just in case, yes, I don't know how deeply everyone here understands. In general, a token can be anything. It can be part of a word. It can be a word. It can be some symbol, and so on. This is how language models work. For example, well, not just language models. If this is, for example, some kind of multimodal model, where some kind of voice input is entered, then the tokens there may be different. For example, there, judging by some sounds, yes, here. Well, then if you ask anything, here.
Yes.
What's the point? What is the problem? Our infrastructure in the world is still old. It says here, Web 2.0. Plumbing cannot handle Web 3.0. Water pressure. That is, we have an old infrastructure where everything works the old way, using the good old technologies that we all remember, which we have been using for decades, and the new AI infrastructure creates new pressure. We want everything to be faster. We want everything to load faster, and so on. But we still here there are three components. I highlighted them as a good example. Let me make it clear right away that all these metrics, yes, 7,000 nanoseconds per operation, these are some kind of local benchmarks. Here, they just, well, show some specific case. That is, this does not mean that in all cases it will have exactly this difference in performance.
Yes.
Here, let's take serialization. I don't know, everyone knows JSON. JSON is a great format, very readable, but it is very slow. And I don't know, you know that, probably most. Many know that data for models is most often stored in float buffers. Here, this is no longer a text format. And you can't read it that easily. Yes, it's binary and, roughly speaking, there are ones and zeros inside. Here, or as an alternative, they use gRPC, protobuf. Here, also much faster. Well, flat buffers in this case, was 10 times faster in the benchmark. This is, a total defeat of JSON. Big overhead. API paradigm. Yes, we are all used to using HTTP, the first version. Here, also in the local benchmark, a tenfold difference is visible. This, I'll say right away. This doesn't mean that this will be the case in all your cases, but it does provide a significant boost if you're using, gRPC, just newer technology.
Yes.
And then I'll touch on hardware memory a little bit. The point is, there's an old concept that we're all used to, using. I don't know, you have a video card. A video card has RAM, video memory. And there is the classic approach to how it used to work. The data was stored in this memory. Yes, it was transferred between RAM, the processor, and, stored in the video card. Here, and the new approach is called LPUs. This is when the RAM is stored on these chips themselves. That is, roughly speaking, they insert it directly into this very a la motherboard. And I don't know why, RAM has become so much more expensive now. Yes, there is a very high demand for this. I was talking about this in the slides before, that token generation. The bottleneck for token generation of subsequent tokens is memory, and a lot of memory is needed. Depending on the size of the model, of course, a lot of memory and context is needed. And there is such a problem. Efficiency also increases significantly. Here you can practically see 10 times. For example, the volume of energy decreases. Yes, there, from 1 to 3 joules per token. Impressive. A good example of, latency optimization. It talks about voice, latency limit. So there is a classic standard method, yes, which can be used to implement some kind of, voice interface. where we embed additional information. That is, RAG. Yes, this is when, as I already said, this is when we, look for something in a vector database. Supplement the data. It could be absolutely anything. Well, in this case, I don't know. Let's say, I don't know, your specific business has some specific knowledge, and you have some kind of assistant there who will tell you with his voice, how you can, I don't know, some kind of agent, yes, who calls, and tells you what services you have, what can be done. And every time a client asks a question, he will search the vector database for some relevant answer. Here, in the old way, and in fact the most obvious and simple, yes, that's how everyone will do it. The agent listens, converts all this into tokens. And then there's this painful stage when it searches the vector database for some relevant queries. Then the ranking process generates the matter. Here, 110 milliseconds. That's what it takes. Again, all of this is kind of, subjective to a specific scenario. Yes, it will not be exactly like that for everyone. Depends on, what the query is, how big it is. I don't know how big the vector database is. There are a lot of different nuances here. But in this case, it shows that in the, new architecture, it was possible to reduce, this latency by almost 316 times. Here, how did you manage to do that? This was accomplished by two agents. One agent is a fast one that runs on the surface. Yeah, which, basically just looks for some, hot some caches in memory directly. And instead of going and searching through a vector database, yeah, if a person said some, I don't know, ask some question that, you know how there is a section on websites, there, frequently asked questions. That is, what you often ask on the site. Caching is very important for AI. And so, very often, not very often, it's actually good practice to use aggressive caching. And caching is used in memory here. And accordingly, in this case, it takes less than 1 millisecond to simply find a specific cache element in memory. Here, I'll tell you a little more about cache too. I don't know if everyone understands this, but the cache here is not a simple one, but a semantic cache. This means that, if the topic is similar in context, that is, it's not just a cache that everyone is used to. We're used to seeing, and we all know, yes, when, for example, there, I don't know, there is, roughly speaking, like some kind of dictionary. Yes, the value key, there, said, hello, and it has some specific answer. This is a very primitive cache, and there is a semantic cache. That is, semantic cache, you can say, hello, and you can say, hello, you can say, there, I don't know, how do you do? And in any case, it will have the same, like very similar meaning. Here, well, and accordingly, the second agent is a slow thinker, prefetching from a vector database. The point is not to wait until the person finishes speaking and giving feedback, but we divide everything into batches. These batches are sent to the back end in advance and processed there. And we start looking for some relevant information in advance about what the user is asking for. While he's talking there, yes, there about his problem, there, oh, yes, I want to, there, I don't know, solve the problem of my business with your services. We are already starting to pull up some relevant documents in advance that might be useful to us so that our voice agent can tell us. Here, big increase. Well, in the end, I will tell you 3 don'ts and do's. What to do, what not to do. First of all, if you develop some kind of real-time agent that communicates with people, people always expect it to work quickly. It says here, keep the path to the model short. That is, all this business logic that you have before work, before the execution of the model itself, should be very short. That is, the less overhead, the less business logic you keep, the better. Do not use old serialization methods. Don't use JSON. Don't use the old classic REST API. Use gRPC instead. Use protobuf. Use flag buffers if possible. Although it is a binary format and more difficult to integrate, it is worth it if you want fast real-time systems. Keep warm state where it matters. That is, whenever possible, use sticky routes to connect to servers so as not to switch or jump between connections to different servers and agents. Use a cache where possible so that, as in the voice agent example, we can immediately access. For example, instead of accessing a vector database, which adds some overhead, we immediately simply look for some semantic cache in memory and provide this information. And, in fact, respond before the whole pipeline finishes. Under no circumstances should you wait until the client has completed feedback or completed some request of his. We start doing this early. This is how all modern real-time agents work at the moment. That is, everything is divided into certain batches. How is it divided? Good question. That is, it can be divided depending on some pauses. That is, when a person speaks, they have some of these micro pauses. This batch is allocated and sent to the back end, where it begins to be processed. Here. And, in fact, don't block your system at every step. Don't wait until it's all over. Stream early. Move slower work into the back end. That is, if you have some more complex function, it should work in the background and also start working in advance. Here, in conclusion, I would like to say that users do not interact with models, they interact with systems. And even if you use the most powerful, the coolest model, the most powerful hardware that exists in the world, unfortunately, it won't help you achieve this cool experience when you don't have a placeholder that loads, and the client waits there, I don't know, seconds, sometimes tens of seconds, which can prompt the client to simply leave the site or, I don't know, the call, the conversation session. Here. Yes, I hope it was helpful. I don't know if you have any questions, please ask.
Super. Thank you, Amir. Very good presentation. If there are any questions, guys, we can take one question. If not, then we'll move on so that we have time to make sure everyone has time to speak, because Andre is next. Okay, well then let's move on to Andre. That's it. Thank you, Amir. Thank you.
Thank you. Can you see the presentation?
Yes, yes, yes. Yes.
Hello, my name is Andrei Serdenko. I work in the field of industrial analytics and computer vision for critical infrastructure at Meteorologic BCS Group. Just a month ago, I was working at Rebellion Photonics, Honeywell, where I was developing gas leak detection systems using spectral infrared cameras. And my presentation is based on this experience. And such spectral cameras allow us to analyze not just an image, but the spectral fingerprint of a gas. We can use special Ballard sensors and local matrices to break the light flow into compounds, into different parts, and with this help determine what gas we are seeing. And what else? This is where boiling gas is used and the area is critical. It does not have access to the internet because security simply prohibits it. Also, because we don't have access to the cloud, we have limited computing power and can't refine the model as we go. And let's move on to the next slide. And very often because of this we see so-called false positives in reality, not in laboratory conditions. And what is a false positive? This is when we have a false positive in the system, when our model, the trained model, misclassifies events.
And even a very good model, which is now Honeywell Photonics. It is an industry-leading model, and its detection rate on average is 85% for detection and 80% for quantifying the amount of gases that were emitted into the atmosphere. It is clear why this happens to us, because the real world is much more complex than laboratory conditions. The weather changes, even the lighting has changed, and the model may already fail. Unexpected factors may emerge. For example, in the picture we see the first example. This is a banal release of steam. And steam has the property that on the spectrum, if we separate it, it absorbs the same amount of light radiation as methane. And it's quite difficult to determine that this is literally true, that we actually have a gas leak and not a false alarm. In the second image, we can see glare, which can also very often act as a false positive, a false alarm. And this is a very pressing issue for marine. That is, when our tower is located somewhere at sea, we have a lot of glare from the sun, and if we simply rely on the model, on the classification, the operator will be overloaded. And it's also important to note that because this is critical infrastructure, a critical area, we cannot blindly trust AI. There should always be a person present to do the verification, and a person does a great job if they are watching 1 or 2 cameras. But if we have a real plant, real production, and there can often be more than 20 cameras, and the operators, if we start to overload them with all these false alarms, they will simply lose confidence in the system, will complain to the manager, and the manager will complain to their sales department that we are getting false alarms, a lot of noise, and we can miss a real gas leak that simply cannot be ignored, and they are often simply obliged, according to recommendations, not recommendations, management, to stop production and conduct an investigation. And we cannot combat this critical problem by simply retraining the model because the physical conditions change. Another one, now that I've moved to meteorologic group, our domain is a little different, but it's still a critical industry, the aviation industry. And what we are currently doing is mainly CNC machines, which are involved in avionics production. We have the same thing. We monitor and track whether everything is going well in the process. The process is automated and human participation is minimal in modern factories. And this example shows that a drop of oil can be perceived by computer vision as a crack or a hardware defect. And when we also have a rotation of a part, this can lead to, we can physically understand the rotation of a part, we can understand what is happening, but if we only cling to a few images, this will give a false alarm, again, and a stop, a halt in production. And this means that the solution must be broader, and given that we cannot further train the model in the process, and it is tied to laboratory training, we cannot simply take some part, or we cannot make an emission, a real emission at the factory. We need to turn to physics. And how do we solve this? This is where we introduce kinematics, a kinematic pipeline. That is, we track physical phenomena, kinematic ones. Kinematics is the science that studies motion in physics. And first we have standard detection using trained machine learning. Next we implemented the pipeline. For the pipeline, the physical pipeline, we need to create a cache again to collect all these motion vectors. That is, it is like a second layer of verification after AI. And it's very important to us because this is computer vision. Motion vectors are very important to us, so we have optical flow. On the other hand, we can't shoot with a lag of 3 to 4 seconds. In reality, we do it for half a second to a second, which is enough to capture 15 to 30 frames and evaluate what is happening. Next, we can immediately reevaluate this. That is, lower the results of the model, that it worked. That is, lower the confidence. It would be great if the company had other sensors that could also be implemented. Sensors, for example, sound sensors are for tunnel checkpoints, vibration or wind sensors. You can even install temperature sensors and various anemometers. And with this, we create a direction in the buffer. We study the speed, acceleration, and we can say whether the AI's decision contradicts the laws of physics. And we move on to the next slide. This is a very simplified formula, the formula by which we do the analysis. Our formula is much more complicated, but essentially, each image is just photons that, if we take just one picture, we can classify something happened here. But if we collect the delta of these images like a series, we can understand, for example, if it concerns glare, we can understand that this is a false positive. Well, not false. The false positive will appear at the end, but we can understand that some movement occurred between the frames. And if we are talking about a gas leak, the gas has some mass, and the gas has a threshold. Even if we have a tornado, the wind will not move at the speed of light. And we, having analyzed 15 or 30 frames, understand the vector of movement, understand the speed and can calculate, the speed of movement and compare. And if it exceeds the threshold, then okay, we lower it. This is definitely a false positive. Further, if we return to steam, we can. Steam has the property that it rises upward due to the laws of physics, and it also has its own speed. And we can understand with the help of a physical model that, okay, we have a constant upward movement, the concentration falls because the steam condenses, and that means this is not methane. We underestimate it and do not give it to the operator. The operator is not overloaded and, accordingly, confidence in the system grows. All these, well, we need to be aware. We need to take into account that all these false positives must be logged and then analyzed.
Andre, I'll interrupt you a little. Yes, let's speed up a little, if possible.
Okay, good.
Thank you.
This is it. This is the last development I have been working on. We use the camera and background assessment to evaluate the gas placement because we're working in 2D. Well, when we look at a picture, it is in 2D, and if we have a leak, we can't tell whether it's close or far, and the AI will say, okay, you have a leak on half the screen. That means it's all over. In fact, there was just a leak close to the camera. And with the latest development, We also used AI classification to study how far away an object is and whether we are blocking anything. If we overlap, we can physically estimate where that scene geometry is. And also with the help of the vector, we can change the masses. We can take into account approximately how much is hidden. So far, our measurements were not very precise, but they significantly increased confidence to 85% from 80. And if we need to speed up, in conclusion, I want to summarize that the main conclusion is that trusted industrial AI in limited conditions must be built not only on probabilities, but also on constraints and validators, which for now must be based on physics. It's just that the world isn't perfect right now, and we can't download all the data that's available from all points, because each enterprise has its own characteristics, and it will never share the data, even with us, the lab. And when we also combine lightweight spatial geometry and time-dependent changes with telemetry, we get systems that operate on limited hardware, conditions, and devices. They are easier to audit and behave noticeably more reliably. And the client's trust also grows because they are based on the laws of physics. And I believe that hybrid systems are the future of industrial AI, and we should not limit ourselves to large models and go for horizontal growth, but try to build architecture with the help of physics as well. And I see time as limited. If you have any questions, I will be happy to answer them. If not, you will get them a little later. Here's my LinkedIn. Please contact me. Super. Thank you, Andre. Our next performance was supposed to be at 12. Then, if there are no questions, we can move on. By the way, all presentations are QR codes. I'll probably think about how to share it with you sometime. I'm recording your conference, so you can come back to all the presentations.
Can I ask a question?
Give me a short and to the point answer.
Super. Thank you very much for your presentation. So, what industries, besides those you mentioned, could, so to speak, benefit from the implementation of hybrid trust systems?
Any that are related to physics. Domain, unlimited domain. Well, computer vision is coming. Educational computer vision. I'm not familiar with autonomous driving. Well, cars, but I'm sure they're developing something similar. But here comes a very important thing in latency and also in frame rate. If you can increase the frame rate, then your model will fire faster. Well, there are strict limitations here, yes, regarding the frame rate. I don't know if I answered the question.
Thank you.
Thank you for your attention. That's it. Thank you. So, let's have our next one. Ilya Toli. Toli, the floor is yours. Oh, and if possible, as I said, for about 12 minutes, so that we still have time, what do you have to insert another slide so that it's possible?
Yes. Thank you. Thank you.
Hello to all conference participants. Now I'm going to talk about a pretty simple thing. I think this is the base. It seems my presentation is visible to you right now.
Yes.
Everything is super. Yes, I will talk about prompt engineering. This is the basic technology, the basic way of communicating with AI. And as a rule, many people can say that this is something very simple and, you can not consider it in detail. But since I deal with a lot of different tasks and I see that, mastering in this matter significantly reduces costs, of the models themselves, and also saves tokens. Well, I've been doing iOS development myself for over 11 years. I am also involved in machine learning and created sections of Wikipedia. There is also a large portfolio of created iOS applications. Lately, I've been working on creating iOS keyboards in partnership with Apple and Android developers. So, accordingly, for different tasks of completely different kinds, I have to work with AI because they, one way or another, offer the best practice. And I can tell you how prompt engineering itself greatly influences the result.
Here.
In general, there are several, ways to communicate with AI. There is often, that is, the most popular way is zero shot. This is when you go to any agent, or there is a chatbot, which you consider to be AI. So, accordingly, you ask a very simple question there. Please give me some weather information. Accordingly, there is no additional data about where you are. The AI might immediately say, I don't understand where you are, so I definitely can't answer you. This is zero shooting. And when you offer certain data to the model, for example, here I am now, there, yesterday I had the weather there in San Jose, such that it was windy there, 15 degrees above zero. Now, please, what will happen today? Accordingly, you offer it some kind of input-output, and the model immediately receives additional data and offers a solution for today based on the same template. Accordingly, such combinations with certain examples allow you to get an instant answer most often. But sometimes this is still not enough. Here, then comes our favorite method. This is a chain of reasoning. This is when we ask a question. The AI can say, I am missing such and such data. Maybe I should do it. Accordingly, you say, yes, please find out the details on this issue. Accordingly, you start a certain conversation. You can go on, there, with a chain of communication for 10 or, 20 dialogues, questions and answers. Accordingly, this is a chain of reasoning, and in the end you have some concept that you initially wanted to see. And the result of the chain of reasoning is, as a rule, the most accurate and desirable. And, well, that is, this is the best option, for the result. But this is not enough, and we have to apply certain templates depending on the incoming data and results. You need to know and understand the model on which the tool is based. Let's say, if we're talking about generating professional photographs, we can't rely on some simple query, like, a man in a suit. Or even you will say, this is done in the style of professional photography, right?
This is not enough, because Azerani has certain best practices of its own for reading prompts. Here. If you know how to write prompts specifically for this model, your results will be much better, faster, and you might not have to try, say, 10 or 20 times to get the desired result without hallucinations. Here, it's very important, well, to figure it out if you want, especially to get results there for 20 different scenarios. Or let's say you're a posting artist and you need to make, say, 20 posts in a certain style today. So, please study the features of each model and name. In photography, it is very important to, well, designate the background, designate which camera, which part you will shoot, so to speak, shoot, right? Because the result is generation, and other necessary details. Also, in the musical sphere, it is important to take into account the mood, to take into account, for example, some elements of musical theory. Here, Because at any moment you can generate completely different AAA moods in the result, you will destroy the entire set of tokens that the AI provided you. It could be bonus, tokens, right? Either you buy these tokens for, your dollars, they quickly get burned simply because you, didn't fall under the most desirable pro-mint architecture. Accordingly, it is imperative to consider the tempo, consider the genre, and, as a rule, AI tools, for example, Suno, offer to show you some examples. Look at examples generated by other people. And you look at their system ones, their point queries, industrial queries. You can copy them. Accordingly, you need to study, and studying also takes up tokens. And you need to save your tokens as much as possible and get the best possible result. This also applies to pictures of completely different kinds, and, naturally, to videos. For video, it is very important to take into account dynamism, take into account detail, and also take into account color change over time and smoothness. Accordingly, depending on the tool, you have to glue different pieces together, and from time to time hallucinations may occur. It's all very simple. The AI model works very well in specific areas, and you need to provide a time frame. The problem arises precisely during the gluing, and you have to form the prompts very precisely so that at the end it doesn't make any abrupt, at the end of the frame it doesn't make any abrupt movements, because when you glue, you'll end up with it ending very abruptly, and the next frame, will be completely, clearly not smooth. And this is one of the most problematic things. Let's say you generate in Grok and, as a rule, in a video editor you will have a big headache, how to glue them together. This is all because the AI itself understands some moments as complete. You need to always imagine what you will do next. Accordingly, you need to have some techniques. It's not just pro-mint that saves this. You need to think in advance about how you will, for example, collect the full result. AA and prompt engineering, that is, prompt engineering techniques also avoid you getting unwanted results in the moment, and also AA in fact checking. Accordingly, and they just give rise to hallucinations. And to get rid of them, you need a grounding technique. As the guys have already said, grounding is a big topic. And examples of grounding, this means that you need to speak or connect certain data in the system prompt. For example, in NotebookLM, AAA, from Google, they have very good ones. That is, they have implemented grounding technology to the maximum extent. You provide sources. You say that these sources contain all the necessary database. Accordingly, every time it gives you a result, it evaluates the already presented down-to-earth facts, and it takes from there and pushes away from it. That is, it creates the final result from it. As a rule, they greatly reduce problems. You can control this grounding data. Well, there are also hallucinations due to the technical problems themselves. The models themselves don't always, so to speak, follow the facts because it's important to understand that AI models can be creatively configured from the start. As we know, the creative model can also be customized. There is the concept of temperature. There is the concept of, let's say, sampling, that is, permitted sampling. You can expand your ability to give less likely things a chance to happen, and this allows you to get a wider variety of results. And it is very important to stick to reality. This problem has not been fully solved. Accordingly, you need to try different prompts and templates. Accordingly, it is very important to study each machine, model for their, so to speak, architectural approaches. How to write prompts correctly. First of all, don't rush to write prompts. Study the model first. And from the point of view of platforms, let's say a coding platform, a design creation platform, it's better to take a few lessons on how to do all this correctly, and this will significantly reduce, so to speak, wandering. Yes, you're wandering during real work. Here, and yes, they provide templates. For example, in Google Skills, there is a huge number of machines, models, and each model has its own characteristics. I have gone through many of them, almost hundreds of lessons, and I see that each time they pay attention to learning different techniques. Accordingly, further, what else can be said? I repeat once again, correct MPTing. Correct writing of prompts saves you time, saves your tokens, and therefore money, and also saves, so to speak, iterations. Iterations, meaning your employees or you personally will repeat the same thing less often to achieve your results. And as a rule, an early result strongly guides you in the right direction. That is, it directs correctly in the right direction. In success, the feeling that AI is really working for you comes to you sooner. Typically, you will try several AIs at once to get results. And it is very important to know how to get results in fewer attempts. In general, if we look at the data types are when we talk about, for example, separately considering photos, photo generation, music generation, video generation, code generation, and also data. This is when we feed this data, feed it into the model. Accordingly, we need to separate it. There's also ChatGPT, a multimodal agent, and also Gemini. They're multimodal. They can accept dozens of, roughly speaking, 4 types of data at once and produce one result. And you can ask for different results. For example, you want to implement something using your voice. You want him to give you a report or a presentation. And these models, accordingly, have a complex structure of prompting. That is, their best practices are completely different, and you need to study and study. Look at how people do it. There's YouTube for that, and there are guides from the platforms themselves for that. And please don't avoid their course. I've already spent, you could say, a lot of time trying to independently derive the best, so to speak, ways of communicating with these models. But it's in vain. Therefore, tutorials, experiment with best practices, and this will save you time. I think that's all. If you have any questions, let's discuss them. We probably have a little bit of time.
Super. You concluded, of course, on a slightly depressive note, so to speak, that you wasted a lot of time. Okay.
Yes. I wanted to say that let's still follow the best practices that the platforms themselves probably wrote for a reason. I, so to speak, checked it from my own experience and tried to approach this creatively on my own. I lost, and I admit that yes, they are not writing all this in vain. And I think that newbies will also naively believe that they can handle it themselves. So let's say it was not in vain. Yes, there is bitter experience. Don't repeat my paths, so to speak.
If possible, share the link to the presentation while we are still here in our now as the final presentation. If you can share it, throw it in the chat. It would be cool so that I don't send it to everyone. And now you've made everyone want to download it.
Yes, super. I'll do it now. Here.
If anyone has any other questions, I can take one. And if not, then we will have a final report from Vladislav in English on the topic of simply AI migration.
Here.
Any questions?
All.
Then let's get moving. Vladislav, the floor is yours.
All.
Hello.
Can you hear me?
Yes, yes, yes.
Everything is fine.
Just a second. Excuse me. It seems that Zoom requires a separate one to share the screen again.
Okay.
Can you see my screen?
Yes.
Great. Thanks a lot. Great. Let's begin. With your permission, I will speak in English if possible.
Yes.
So my name is Vladislav. I spent last decade architecting system for big retail companies, and I want to talk about something that's fundamentally changing our field. Gen AI can now analyze your code base and recommended architecture changes in minutes. The number here basically are real. AI tools are handling now from 69 till 75% of the code added during the modernization projects. So that's not a future projection. That's happening right now in the production systems. These tools cut basically project timelines by 35%. What used to take a year now takes basically 8 months. But here's the catch: the AI can't see your business constraint. It read your code brilliant. It doesn't read your business itself. So the question this talk answer is, when AI recommend architecture changes, how do you decide what to follow, what to modify, and what to reject? That's what we are going to explore today. Next slide. So first, let's establish what AI can and cannot do for architecture today. AI capability are genuinely impressive today. It can basically parse millions of lines of code, identify architecture patterns and anti-patterns, suggest model architecture, microservice service, cloud native, calculate performance metrics, estimate cost and timeline, generate detailed migration plan. This is remarkable technology that and this capability basically would have been considered more like impossible 5 years ago. But here's a critical gap AI cannot see. Your business model, your regulatory constraint, your operational reality, your organizational culture, your team's actual capability, the hidden costs that are specific to your business, to your context, your political dynamic. AI is trained on massive data sets of code and architecture patterns, but your business context and your specific constraint, basically, these things that make your situation unique, that's the points that are unknown by AI. AI can see any of that. It's reading your code. It's not reading your business itself. And that gap has destroyed basically more modernization project than we can count. Let me tell you about one that basically almost happened in one of the big retails that I work with. Next slide. So we are talking about one retailer that has basically thousands of stores globally, over 50 countries. They have a legacy point of sale system that needs modernization. Leadership being smart, they bring multiple AI architecture analysis tools. These tools basically analyze the entire code base, and the AI comes back with a recommendation that sounds fantastic. Full cloud migration, microservices, modern architecture, here benefits, 40% better performance, 30% lower infrastructure costs, 6-month timeline. The business case looks incredible, and the board basically almost announced the start of the initiative. And then basically one person from the room just asked, okay, but what happens when a store loses the internet connection? Because that's question relevant, and it is something that opens something critical. These stores, they're in over 50 countries. Some locations have unreliable internet, rural areas, area with infrastructure issues, or maybe internet outage during storms. And if a POS system is cloud only, if internet goes down, the store basically cannot process transactions, cannot take payments, cannot ring up sales, so the store is effectively closed. We calculate the risks and send up like in 44 hours of outage per year on average at $45 per transaction, 50 transactions per hour per one store, 3,000 store, it's like $6.75 million lost for hour of outage. Multiplying that with the 44 hours per year, it's almost $300 million in potential loss. They just recommended an architecture that would have been cost this company nearly $300 million in loss. They wasn't being malicious. It was doing exactly what it was designed to do: optimize for code elegance, cloud benefit, modern architecture patterns. What it could not do was understanding the stores must work offline. It's not preference, it's a business survival requirement. Why I missed critical constraint? Here is the core problem with the AI architecture recommendation. And AI treats everything as trade-offs. Should we optimize for performance or cost, security or usability, speed or reliability? That's a trade-offs. You can balance them, you can negotiate. But some constraints are not really trade-offs. They are boundaries, hard lines that you cannot cross. We call it this constraint like business invariant, non-negotiable constraint. If your architecture violates one, it doesn't just perform poorly, it basically fails completely. We found that they usually are falling in a couple of categories. We identified usually we have 4 of them. One are regulatory, like GDPR in Europe, that says the customer data must stay in Europe. Not should, but it must. Second, operational. This comes from your business actual operate, must work offline for that particular retailer. You might say cloud only is optimal, but it makes your business non-operational in common scenarios. Third one, business model. This comes from how you make the money. Maybe you need sub 100 milliseconds latency for real-time transaction, not 200, not 150, because that's what basically SLA promises. Without it latency, basically could lose again customers. The fourth one is the integration itself. This came from system you're looked into. Maybe you have like 20 years old ERP that runs payroll for 50,000 employees. And I could say that you can replace it for clean architecture, but that's not happening. There is a fact of life for this company. Now, here's the critical thing. AI tools cannot extract these invariants from your code. They are not in your code base itself. They are in your business context, your operational, your legal requirement, your organization realities. You have to identify them, and then you have to check every AI recommendation against it. But that's not only part of the problem. Also, AI cannot at the moment calculate exactly all the costs. On the next slide. Here basically is how people evaluate AI recommendation. For example, it shows you benefits, the great benefit, plus 40% in performance, implementation in 6 months, and 2 million to implement this project. The benefit minus implementation costs is the benefit bigger or smaller. That basically it's a simple math. The formula is missing something massive that AI usually is not showing. What AI basically doesn't calculate is a persistent operational cost. For example, you need to hire a new senior, or complexity. You are managing 47 services instead of 1 in case of cloud migration. Debugging. Incident that took basically 30 minutes to resolve now could take 3 hours because you have tracing across thousands of services. Learning. The team doesn't know distributed system. Productivity drops. Training take months. Risks. More moving parts means more things to break, and distributed failures are hard to diagnose. Another one also is lost capabilities. You had a simple AC transaction, now you have eventually consistency, you have easy debug, now you have distributed tracing challenges. I show you the numbers, the benefit, the good stuff. What it doesn't not calculate is denominator, all those ongoing costs. And when you actually calculate the full equation, benefit minus implementation, minus persistent cost, minus risk, minus loss capabilities, sometimes the great recommendation turns out to be a negative value. A real example is, again, one retailer. The company breaks their monolith into 47 microservices. First year, it was really great. It received the fast deployment, the one that they, let's say, wanted to have for many years. But after that, in the second years, the team is burned out. The on-calling is nightmare. They're hiring more people just to keep the lights on running a system. The total cost of ownership went up. Next one. Working with AI nowadays, basically, we had, and I designed a pretty simple framework that basically helping us to achieve together with AI a better solution. It's a 3-step framework for evaluating AI architecture recommendation. It's a simple, practical, and it's prevent expensive mistake. Step 1, extract business invariant before you look at the AI. Before you run any AI tool, before you see any recommendation, gather your stakeholders, business, operational, legal, tech. Ask them what would cause business failure if violate. You'll get like 20 or 30 things initial, then refine. It's not non-negotiable or just strongly preferred. you will end up at the end to have like 3 to 7 true invariants. For this particular retailer, for example, we've identified store must work offline, must integrate with SAP ERP, must comply with 50 plus countries regulations, must handle Black Friday traffic spikes, must respond under 50 milliseconds. The second, check AI against invariants. Now run your AI tool. Get the recommendation, review the benefit, they'll basically impress. Test. Does this recommendation violate any invariant? Be honest here, if it violates one, the recommendation is invalid at all. Doesn't matter how optimal it's claimed to be. Third step, calculate the true value. The value basically that we're talking that it's not just total cost minus spends. For recommendation to pass, you need to calculate the full cost, not just benefit. Benefit minus implementation, minus persistent cost, minus risk, minus loss capabilities. If the result is negative, reject it or significantly modify it. This step takes maybe 1 or 2 days of work, but prevents 6-month projects to fail. So back to the retailer that we just discussed about. We had a problem. AI said full cloud migration is optimal. Business invariants said must work offline. But here ways AI suggestions and human judgment combined to create the right solution. We built an architecture, a hybrid architecture. Let me explain what that basically exactly means. Every store run locally, local instances of core services on premises, transaction processing, payment handling, core post functionality, everything critical that need to work during the outage. In the cloud, we run only centralized management, analytics, reporting, inventory synchronization, non-critical services. When store have internet, they sync with cloud, get updates, push data, leverage cloud capability. When internet goes down, they keep running locally, completely independent. The QR is updated. When internet comes back, they sync back up. This architecture basically respects the offline invariant. Store without internet is working. Use microservices. We got the AI suggestion here. Leverage cloud for scalability to handle the Black Friday traffic, for example. Preserve all capability, offline operation maintained. We got the modernization benefit AI recommended, and we preserved the business critical capability. AI showed microservice was the right architectural style. Business invariant showed us we need a hybrid deployment. Both were necessary for the right answer. If we followed AI blindly, store shutdown during outage basically costs hundreds millions for that retail. How to work with AI? I want to be very clear here. Basically, the talk is not like anti-AI. AI is incredible value for architecture today. The future isn't AI versus architects. It's AI partnering with architects. Here, what AI basically provides: pattern recognition across thousands of code base, technical optimization suggestion, speed analysis in minutes instead of weeks, best practices synthesis, trade-off calculation. This is generally powerful technology. Here's what you have to provide together with these options that AI is suggestion. You will have to provide the business context identification, constraint extraction, true value calculation, risk assessment, and the most important one, the final decision authority. AI provide technical optimization and speed, and you provide business context and judgment. Together, better decision faster than the cloud make alone. In the age of Gen AI, your value as an architect isn't diminished, it is elevated, because someone needs to know which AI suggestion build the value and which destroy it. Someone needs to bridge the technical optimization with the business reality. Your action checklist. Okay, so some practical takeaway from this. Next time I recommend architecture changes. Here's exactly what and how basically we should behave. First, we have to extract the business invariant first. Before looking at the AI recommendation at all, get stakeholders in the room, ask what would cause the business failure to implement 3 to 7 constraint. This take like a few hours or a day or two. Second, get the AI recommendation. Run your tools, read the suggestions, understand the benefit AI is calculating. Third, check compatibility. Does the recommendation violate any invariant? Be brutally honest here. If yes, you must basically modify or reject some suggestions. Calculate the full value. Don't just accept AI benefit estimates. Adapt implementation cost, persistent, operational cost, risks, loss capabilities, and so on. And fifth, make your decision based on evidence. Follow it. If passed, I'll check. Modify if core idea is good but need constraint. Reject if it violates critical invariant. What not to do is basically don't accept the recommendation without invariant check. Don't ignore ongoing operation cost. Don't override business reality with the best practices. Don't assume AI understand your specific context, your specific business rules, and how you are doing money. Don't skip stakeholders conversation. This gives you basically plus minus 3 possible outcome. Follow, it's about 10%, and recommendation and compatibility and value is clear. Modify, most common, it will be around 70%. The core idea is good but needs some business constraint to be added. And reject, around 20%, when it violates critical invariance or true value is negative. These 5 steps, they prevent 6-month project to fail. They prevent you from destroying the business value while thinking you basically improve the system. And the future of architecture in the age of AI. In the age of AI, your value as an architect isn't diminished, it's elevated. AI can suggest, you can decide. And decision-making capability, grounding in the business reality, not just technical elegance, is more valuable than ever. We are entering in an extraordinary area. AI can analyze millions of lines of code and suggest architecture in minutes. That's not replacing architects. That's changing what architects do. 3 takeaways. 1, AI is powerful but incomplete. Use it as an advisor, not as an oracle. 2, business invariant are non-negotiable. Identify them first before AI basically is trying to suggest any modification. And the 3rd, calculate true value benefit minus all the cost, including the hidden one that usually AI is not aware of. The future needs architects who basically will partner with AI efficiently, identify constraint AI can see, calculate cost AI doesn't know about, and act as a decision maker that preserve business value to the business itself. I think that's it for me. And by the way, here also is a QR code for my LinkedIn if you like to ask some question too.
Thank you so much for the talk. It's very informative, a lot of information to process. Really appreciate it. Yeah, so if you guys have any questions or comments or concerns, feel free to ask them. We have some time here, maybe a couple more minutes, and we're going to close out
Thank you for your speech. Can I ask a question, please?
Yep.
How do you make the case to stakeholders that waiting is actually the riskier option?
Sorry, I didn't follow the question. Can you repeat once again?
How do you make the case to stakeholders that waiting is actually the riskier option?
The key point here basically is to document everything, to provide your point of view and to document the risks. If basically they are thinking it is an optional, then basically all these constraints have to be documented and replied back to them, so they will sign on them. And if in the future basically you will be questioned why it happens, you basically have the right argument that basically from the technical point of view, you analyzed it correctly, you've documented everything, you've provided the risks and the possible outcome for that. But the business decision in the final end, it was that we need to follow, even if you know this, let's say, red log, that this risk was in place. And in this way, basically, it's already the side of the business to decide and to take the responsibility of their decision.
Okay, thank you very much.
You're welcome.
And one more question, please. Do you think AI will eventually replace the platform or DevOps engineers, or will their role become even more important in their future? Thank you.
So let's say, I think the AI will replace the stuff that basically are programmatically, the stuff that basically that easy to automate, where you have exact steps and you have to follow a specific pattern how to finalize a task or something like that. But from my point of view, I think it will never replace the job or the part of the work that involves judgment, because where the judgment is involved, it's not only judgment. Back with judgment basically is the responsibility. AI will not take responsibility for a specific part, for a specific implementation or a change. Here basically is the point where a person that will provide judgment and responsibility together, basically, those person will not be replaced. The ones that just are working like moving forward based on a specific written steps, these jobs and part of the work more likely will be replaced, from my point of view at least.
Thank you.
All right, maybe one last question from me. You mentioned, you spoke about a lot of things in the presentation. So what would be the main takeaway from your presentation? Like, what do you think the most important thing that everyone should take away from this?
Yeah, the most important point I would say is this collaboration with AI. Previously, the architects basically was acting like more technical people that basically are designing applications and basically providing more technical details. Today, basically, the architects will become more like a judge, like a decision maker, and the architect basically will be the real bridge between technical part and the business. And we don't need to fight with AI. We need basically to learn and practice to work together with AI. In this way, basically, we'll provide more value and we will be, let's say, important in our places. If we will try to fight with AI, I think we will be replaced pretty soon.
Thank you for your answer. Great presentation. Any more questions, you guys, or we can close out?